It is our 10th online lecture for reliability engineering. Mm, so before we start, I would like to first mention that last week the lecture was given in a recorded form. So, and it covered the lecture of the last week covered chapter 3 of our textbook. So I would like to first ask whether there are any questions about last week's recorded version, recorded lecture. Or if you felt any difficulty or if you felt uncomfortable with that recorded version of the lecture, then please let me know. And so, because we did not cover the problems, or of course, 2 weeks before we had a midterm exam. So this was the problems that you solved uh, for the midterm exam of reliability engineering. So you had 3 hours to solve this problem, and you were allowed to refer to our textbook, and also you could do any search, Google search or any search, and all the information in the internet was available to you. And also, as I already mentioned, you had 3 hours, and you also had all the mathematical tools like MATLAB or Microsoft Excel or any other tools that you prefer. So when I prepared the midterm exam, I also considered all these factors and tried to develop some problems with consideration of all this available information to you, available information and tools to you. So if we see the problems briefly, review the problems one by one. The first problem is about calculating the probabilities. And so this problem, for this problem, you to correctly solve this problem, you need to clearly understand the meaning of independent events and mutually exclusive events. In case of number two, so unfortunately, it was later found that the distribution, the function, the form of distribution is not complete. So in fact, we need to. This one is I do not know why, but t is currently missing here, and also I needed to square the log of t. Yeah. Uh, at this point. So it should be exponential to the power minus 1 over 2, and log of t squared should be the correct form of equation for, in fact, log normal distribution. And so there are some different responses from the students. So some students simply did not even try to solve the problem, and some students also, many students also indicated that this equation for the distribution is not complete. There are some problems in this equation. And also, there are other students that not only indicating that this equation is problematic, but also uh, tried to solve this equation by simply attaching t inside of attaching, so placing log of t with the assumption that this one should be log of t. And other students also recognize that the initial intention is to provide the probability probability distribution for probability density function for log number distribution. So recognize that changed this to log of t squared and then provided all the answers for the four questions. So after seeing all these different responses from the students, what I thought is that all these answers cannot be treated equally. So for those students who actually corrected the distribution, recognized that this is the distribution for log normal distribution, and then provided all the answers. And in that case, that should receive the highest score. For those students who simply indicated that the equation is problematic, then in that case, so I should provide some. Of course, it is good. It is good to indicate that, but I cannot provide an equally high score to those students who simply indicated that the equation is problematic. And also, I already mentioned that there are some students who did not even think about try to solve this problem. So I decided to provide different scores for all these different responses. So of course, initial intention was that I intended to provide the log normal distribution, and I wanted to find the mean, median, mode, and variance of this log normal distribution. And in case of mean and variance, you are able to find it in the textbook. In case of median and mode, of course, the definition of a median and mode is provided in the textbook, but in this case, so maybe you can do some internet search, and if you look at the page, the Wikipedia for log normal distribution, then you will be able to find how to find the median and mode of this distribution. So because all this information was available to you. So this mode, and so of course mode is the point where the PDF has the highest value, the maximum value, and mode median is the place that the cumulative distribution function becomes 0.5. So I think you will be able to find all this information. And if you know this information, then it was not that difficult for you to calculate that. So that's for equation and problem number 2. In case of problem number 3, so xi is the random variable for the outcome of rolling ith die, and yn equals, so it is asked that you should calculate the kind of expected average. In fact, it is a distribution. So as xi's are random variables, in this case yn is also a random variable. So this is the distribution when we roll 2 dice, 3 dice, and 5 dice. So, in case of 2 dice, then of course there are only 36 cases. So, it can be calculated by enumerating all possible cases. In case of 3 dice, of course, there will be 216 cases. So also, still it is possible. And also some students also tried to enumerate all 216 cases and then find out this distribution. But in case of Y5, I think starting from Y5, it is very hard for finding the distribution by enumerating all possible cases. So from this point on, you need some mathematical background to provide answer for this. So I wanted to see whether you have enough enough knowledge or enough ability to provide answer for this. So this is actually the distribution. This is the case when there are only 1 die. This is the case of 2 dice. And this is the case when there are 3 dice. So this is the distribution for 5 dice. And of course number 6, the problem 6 also asked you to find out Y10. And here we have sorry. So here we have this is the distribution for Y equal Y10. And we may increase the number of dice to 20, 50, and 100. And in fact, this figure, these distributions are also related to what we covered last week in normal distribution. So this is related to central limit theorem. So starting from any distribution, as we increase the sum, as if we add, so if we increase the number of dice, or if we increase the number of distributions equal the same distributions, but in that case, if we calculate the average value, so we add all the numbers from the distributions, from n distributions, and then add them, and then divide it with the number of distributions, or the number of random variables. Then what we can see is that gradually the distribution follows a normal distribution. And that is the meaning of a central limit theorem. So initially the distribution was a uniform distribution, but gradually as we increase the number of dice, or the number of random variables, the number of distributions, then gradually the distribution follow a normal distribution. And there are a few students who were even able to calculate the case when there are 10 dice. So number 4. So I provided a text file which includes 300 sets of random samples from a normal distribution, and each set contained 10 samples. So overall, I provided 3,000 numbers. So in the first, I wanted you to calculate the 95 confidence level for population mean and also 95 confidence intervals for population variance. So I realized that only a few students and provided the 95% confidence intervals for variance. Of course, many students tried to provide the 95% confidence interval for population mean, but they usually did not provide answer for population variance. And drawing a bar chart and with the data, I wanted you to actually count the number, count whether 50 was included in the 95 confidence interval. So the expected, so because the 50 and 100 is in fact the population mean and population variance of the original normal distribution, and the expected number uh, expected probability of this 50 being included in this 95% confidence interval is actually 0.95. That's why it is called as 95% confidence interval. And similarly, the expected probability of 100 being included in 95% confidence intervals for population variance was of course 0.95. So if you count the numbers, and then it would be it would be around, not exactly 95%, but a number very close to 95%. So in case of a number 5, and also to solve, for you to solve the problem, that you needed to have some sort of skill to handle large numbers of data. In case of number 5, this was the data from table 2.4 in our textbook. This data is for example 2.31. So they are expected. It is generally expected that you are able to at least solve this problem or handle this amount of numbers. And I simply provided different intervals to perform chi-squared test. So if you are able to understand, what chi-squared test, and if you know how to apply chi-squared test step by step, then you could be able to find the conclusion for this problem. And to see whether this hypothesis should be rejected or not. So, is there any question about our midterm exam? If you do not have any other questions, and let's see. Sorry. Okay. So before talking about before move to chapter 4, let me just briefly talk about first chapter section 2 point. So 3 point. We last time we basically covered section 3.1 and section 3.2, the concept of reliability and common distributions that are used in component reliability. And those distributions are, I hope you are already familiar with these distributions. The distributions are like exponential distribution, wave distribution, log normal distribution, normal distribution, and so gamma distribution, and so on. So the distributions that we already basically learned in chapter 2. And if we go to section 3.6, 3.6 is about Bayesian estimation procedure. So it would be good if we are able to cover this section, because later you will realize that. So if you pursue an advanced courses, so then this Bayesian estimation or Bayesian update is a very important concept if you do some research. But in fact, of course, but this, what is written in this, of course, starting from this equation, what is written here and described here is somewhat complicated. So I was afraid whether all the students might be able to follow if I give lectures on this topic. So I decided to skip this part also. And instead of that, I would like to give you some example, some video clip that may help you what is meant by Bayesian update. So they are playing a poker game. So basically they are playing a poker game, and what you can see here is that the probability of each person, the winning probability, the probability of a win for these two people. So in this case, the first one has the probability of 56% of winning. Second person, 43%. And so at this point, the cards will be opened. So in fact, now we can see 3 cards are opened to the players. This is a kind of new observation that we make. Previously, we did not know what these 3 cards are. But at this point, what we realize is that the 3 cards are Diamond 8 and Spade 2 and Clover 6. So we made a new observation and we received a new information. So that information will change these probabilities. So now the probabilities are now changed to 71 to 29. So the probability change was made because we made these observations. And in fact, the Bayesian inference or Bayes rule can be applied to update all these probabilities. And currently we do not know the fourth card and fifth card. So depending on what they are, the probability will also change. Okay, now what we just observe is that the fourth card is spade Q, and these probabilities are further changed based on the observation of the fourth card and based on the information that is provided, the new information that was received. The probability distribution is now changed. And if the fifth card are revealed, then of course we are definitely determine who is the winner and who is going to lose. So this explains the very basic concept of Bayesian update and the concept that the probability update after make some observation or after receiving new information. And of course that Bayesian process is in this case applied to a continuous probability density function, but maybe this one, the theory for Bayesian estimation can be too complicated for undergraduate courses, so this one will be also skipped, and we are going to move on to chapter 4. So if you are interested, then of course I highly recommend you to read what is written in section 3.6. So we are going to learn about system reliability analysis. In chapter 3, we covered the definition of or the meaning or definition of reliability, and then all the distributions that could be used to describe component reliability. And in this chapter, in chapter 4, we are going to combine the reliabilities of components and try to calculate the reliability of a system. So let's see one by one. So first example, so we are going to talk about chapter 4. Let me write down the title of chapter 4. Chapter 4 is about system reliability analysis. So at this point, we are going to assume that we know the reliability function RT. So RTs. So reliability function of all the components in the system. And then now we are going to try to calculate the reliability of the system. And section 4.1 is about reliability block diagram method. Reliability block diagram method. The first case, series system. So figure 4.1 show us an example of series system reliability block diagram. So, and we are going to assume that reliability functions for all these n components are already given. And we would like to calculate the reliability of the whole system. So from the very basic characteristic of a series system, if anyone fails, then the system will fail. So that means for the system to work correctly, then all the systems, all the components need to work correctly. All the components need to perform their intended functions. So in case of a series system, so reliability, so basically the series, in this case of a series configuration, all items must function successfully. So how can we calculate? In this case, the reliability of the system, in this case, the reliability of the system and reliability of system as a function of time equals the reliability of the first component as a function of time and the reliability of the second component. Reliability of second components, and we are going to multiply all these reliabilities until the last one. The last one is the nth component. So basically what we need to calculate is the product when I equals 1 until I becomes n, reliability I should be placed here. So in case of a series system, the reliability of the system can be calculated as the product of the reliabilities of all components. So in this case, how can we calculate the hazard rate? So so hazard rate is denoted as S, and in this case, because hazard is also closely related to failure rate, so in this case we are going to write it as so we are going to introduce this new parameter called lambda s. So this is simply this one also, lambda s is also intended to indicate the hazard rate. So how can you calculate the hazard rate? So from the lecture of last week in chapter 3, hazard rate is basically defined as ft, that is probability density function, divided by reliability function, reliability. And so we have a 1 over reliability multiplied with ft. So what is ft? ft is in fact the derivative of cumulative distribution function with respect to t. And I hope you remember that the reliability RT, so where reliability is given as 1 minus cumulative distribution function. So that means if we differentiate both sides, then it can be found that df dt equals dr minus drt minus drt dt. And if we have 1 over r multiplied with dr dt, so that is the same with if we differentiate. So if we differentiate log of RT, then we are going to get the same expression here. So this will be same with this is the same with log of RT log of RT dt. So if we know, because we know what is given here, so RT is given as the product of reliabilities of components. So if we take both sides with natural log, then log of RT is going to be log of, so it will be, so log of RT will be same with, this will be same with I'm sorry, log of this. And maybe, of course, at this point you know what we should do. Log of all these products will be same with sum of all log. So this will be same with the sum of from I equals 1 until it becomes n, and a log of RIT. Log of RIT. And so if this is the equation for, this is the hazard rate for the system, then each one, of course, this will be same with, I'm going to take the sigma here. So it will be same with this. And each one, d log of RIT dt will be the hazard rate of individual component. So that will be same with the sum of all lambda IT. So if lambda indicates the hazard rate, Or we may write HIT if the hazard rate of an individual component is written or denoted as HI. So in this case, we use the lambda I to indicate hazard rate. So if constant hazard rate, if hazard rate is constant, then lambda I will be a constant. So in that case, lambda S will be also a constant. So lambda S is going to be simply the sum of lambda i's. We are able to calculate so if the hazard rate is given, and we are able to calculate mean time to failure. Of course, the definition of a mean time to failure is the integration from 0 to infinity, and we multiply time and ft dt. And if ft, so of course this f should correspond to the f of the system. So in this case, the f of the system will be lambda s exponential minus lambda st. So if we write it here one more time, then it means fst should be lambda s t lambda s exponential minus lambda st minus lambda st. So if you actually perform the integration, then we haven't seen many times that the final result that we are going to get is, so lambda s should be placed in the denominator. So mtts will be given as 1 over lambda s, and this will be same with, because lambda s is given as a sum of all lambda i's. So these are equation 4. So we just covered all the equations from 4.1 to 4.5. So I'm going to add subscript s to indicate that this is the mean TTF, mean time to failure for the system. So in case of series system, then the equations are relatively, I would say, simple. So the reliability is given as the product of all reliabilities of components. And in case of a hazard rate, and if hazard rate is, in case of a hazard rate, will be calculated by adding all the hazard rates of all the components. So when constant hazard rate is constant, in fact this is the case for exponential distribution. So if the hazard rates are all constants, then the system hazard rate is also given as a constant, and mean time to, in that case, of course, reliability will be given, reliability function will be given as exponential minus lambda st. So let me add one more line here. So in this case, of course, if you would like to calculate the mathematical equation for, or mathematical expression for the system reliability, so that will be given as exponential minus lambda s minus lambda st, and mean time to failure is calculated like this. Oh, also one more thing, that previously it was also mentioned that, of course, this is the definition of mean time to failure, and mean time to failure should be calculated like this. But in fact, another way of calculating mean time to failure is to, so previously it was already, I mean, in chapter 3 last week I already showed you that the integration from the, if we integrate the reliability function from 0 to infinity, then we are also able to calculate the mean time to failure of the system. Of course, in this case, we should use the reliability of the system. So because this is exponential minus lambda st dt, so in this case it is much easier for you to find out the integration of this exponential function, and of course we will get 1 over, we are going to get the same answer. So the mean time to failure can be calculated either way. If you are able to, you may integrate it. In this case, you should apply integration by part, or you may so after applying the integration by part, we derived this equation, and you can directly use this relation. So we are going to move on to section 4.12 about parallel system. So in case of a parallel configuration, only when all blocks or items fails, then the system fails. So let's first see on figure for the parallel system. So if there are n components, and if it is assumed that if any of n components perform its intended function, then the system is also okay. System also is able to perform its intended function. If that is the case, and of course in case of a safety system, we utilize this type of configuration very frequently. So in case of when we launch a space shuttle, and there are some computers that performs some important calculations for the flight. Then we, in that case, we place not only one computer, we place several computers that performs the same function. So if any of that redundant computers are working, then the system will be fine. So that is the case for parallel configuration. So in this configuration, the system is able to, or the system fails only when all the components fails. So in case of series system, in this case, the system will be operating correctly only when all components function successfully. In case of a parallel system, so I'm going to bring and copy this relation and then modify this. So in case of parallel system, f, the cumulative distribution function, or the failure probability, the failure of the system, the failures of the system is only possible when all components fails. When all components fails. And in fact, this 1 minus f is in fact same with 1 minus reliability of 1 minus reliability. So how can we calculate the reliability of the system? Is given as 1 minus FST, 1 minus failure probability, and therefore it is given as 1 minus and the product of 1 minus RITs. So that's equation 4.6 and 4.7. So if the system with two blocks and failure rate are constants. So once again, this is the case for exponential distribution. So failure rates are constants. Means the meaning of the failure rates are constants is that so reliability of a component is given as exponential minus lambda IT. So in this case, lambda ST, the system reliability, is given as 1 minus so from this equation now there are only two components, so that means we should calculate 1 minus and 1 minus R1t and 1 minus R2t. And RIT is given here. So R1t is exponential minus R1t, and R2t is exponential minus lambda 2t. So we have 1 minus lambda 1 I lambda minus 1 1 and minus exponential minus lambda 2t exponential minus lambda 1t plus exponential lambda 1 plus lambda 2t. So what will be remaining? This one will be cancelled with this one, and what will be remaining is plus 2 minus lambda 1 plus lambda 2. Lambda 1 plus lambda 2 t. So that's equation 4.8. So if we would like to calculate the failure hazard rate, if we would like to calculate the hazard rate of the system, so once again, I already told you that hazard rate. So before calculating hazard rate, let's first calculate the probability density function first. Because when we calculate the hazard rate, this probability density function should be placed in the place of numerator, while the reliability will be placed in the denominator place. So if this is lambda s, so once again, the fs, the probability density function, is given as the derivative of cumulative distribution function. And because this fs is given as 1 minus RT, 1 minus reliability of the system. So this is same with minus of reliability of the system. So reliability of the system. So if this is the reliability of the system, then if we differentiate the first term, what we are going to get is lambda 1 exponential minus lambda 1t. So the first term, lambda 1 exponential minus lambda 1t. The second one, lambda 2 exponential minus lambda 2t. And the third term, minus lambda 1 plus lambda 2 exponential minus exponential to the power minus lambda 1 plus lambda 2t. So if we calculate this, then we are able to now find out the relation for the hazard function. So this is the function for the probability density function, and this is the This is the system reliability function. And this becomes the hazard rate or hazard function. So previously, in the case of course, if it is preferred that we may denote this as lambda st. So in case of the series system, we denoted HST as lambda st. So, and this is equation 4.10. And next, how can you calculate? Here's here. Mean time to failure. So mean time to failure, of course, this is the basic definition. And I also told you that if we perform the integration by part once, then we are going to get this relation. So mean time to failure can be calculated by integrating the reliability from 0 to infinity. So that means we should integrate this. Then the first term will be 1 over lambda 1. The second term is 1 over lambda 2 minus 1 over lambda 1 plus lambda 2. So that's equation 4.11. So what about when there are in the case of a system with n parallel blocks or parallel items? So then what will be the reliability function? So that is going to be exponential in case there are 3, then exponential minus lambda 1, lambda 2, and lambda 3 minus exponential minus lambda 1 plus lambda 2 minus lambda 2 plus lambda 3 minus lambda 1 plus lambda 3 and plus exponential minus lambda 1 plus lambda 2 and lambda 3 will be the reliability function. So if we calculate the MTTF, then what we are going to get is 1 over lambda 1 plus 1 over lambda 2 plus 1 over lambda 3 minus 1 over lambda 1 plus lambda 2 minus 1 over lambda 2 3 minus 1 over lambda 1 3 and finally plus 1 over lambda 1 plus lambda 2 plus lambda 3. And if we have more than that, so once again, what I'm telling you is that in case we have 3 components, what we are going to not 3, so In case we have n components, then first we add all 1 over lambdas, and then so in case of there are 3 components, then the first one will be 1 over lambda 1, 1 over lambda 2, and 1 over lambda 3. And the second one is minus 1 over lambda 1, lambda 2, lambda 2, lambda 3. Let's write it as 1 lambda 1, lambda 3, lambda 1, lambda 4, and so on until it becomes 1 over lambda n. So if we add all the 1 over lambda 1 and lambda 2, 1 over 2 lambdas, and the final term will be 1 over lambda n minus 1 plus 1 over lambda n. And then plus we are going to add all possible cases of with 3 lambdas and 4 lambdas and so on. So this one should go on and on until the last term will be minus 1 to the power n plus 1 So wherein there are 2 terms, then this one should be minus. When there are 3 terms, the last term will have the plus sign. And in case of the last term, it should be lambda 1 plus lambda 2 plus we are going to add all the terms until from lambda 1 to lambda n. And this is going to be the mean time to failure of the system. When all n units are identical, that means all the lambdas are same. Lambda 1 equals lambda 2 because they are all identical components or item. This is simply given as lambda. So if this is the case, then let's first talk about lambda is reliability of the system. So let's use this relation. So reliability of the system for parallel configuration is given like this. This is the basic form of equation, and if Ri is all given as exponential minus lambda I lambda t. So I better use a parenthesis instead of this bracket. And we are going to multiply this n times. That means we are going to get the power n. So this is the system reliability, how the system reliability is given. And how can you calculate mean time to failure of the system? So mean time to failure of the system. So of course, if we place all all lambda i's into replace all lambda i's with lambda, then we will able to calculate the mean time to failure. But in that case, the procedure will be more complicated. So in this case, it is better for us to directly attempt to calculate the mean time to failure of the system. So once again, this is the equation for calculating the mean time to failure of the system, and we know what lambda st, the reliability of the system, is. So reliability of the system is given. Take the bracket, and so we should calculate this. And if you think calculating this would not be easy, then what I can tell you is that you may try. You may try, or you may substitute exponential minus lambda t with some another parameter. So so let's put u as exponential minus lambda t. Then du is given as, if we differentiate the right hand side, then what we are going to get is minus lambda exponential minus lambda t dt can be found. So dt is given as du divided by minus lambda e exponential minus lambda t. So what you can follow is that so I think we do not need the bracket anymore, and minus lambda, so minus, and lambda should be placed here because it is a constant, and exponential minus lambda t should be placed here. And in fact, this is the same with u, and 1 minus exponential minus lambda t, this is also u, and also this is du. T is t when t equals 0 this is going to be 1, and when t approaches to infinity, u will approach to 0. And we are going to hmm, hmm. Well, so I'm going to introduce x as 1 minus u, but what I just realized is that we could define u as exponential minus lambda t. Instead of this, we could define u as 1 minus exponential minus lambda t. So anyway, if we define x like this, then dx is going to be minus du. So instead of u, we are going to have 1 minus x. Instead of 1 minus u, we have x to the power n. And minus will be deleted. This becomes x, and integration starting from not from 1 to 0, now it becomes from 0 to 1. So if you know what 1 minus xn, x to the power n is, so it has 1 minus xn plus many terms. So what we are going to have is, so it has 1 minus xn, 1 plus x squared plus until x to the power n minus 1. So what we are going to get is 1 over lambda, and if we integrate 1, then we are going to get 1. If we integrate x, then 1 over 2 and integration from 0 to 1. That is going to be 1 over 2. In case of x squared, if we integrate x squared 1 over 3, and then x cubed will remain here. If we apply 0 and 1, it will again becomes 1. So this is what is going to remain. So eventually n minus 1 will, I'm sorry, from n minus 1, so it should be 1 over n. So this is what is given in equation 4.14. So what I just, as I already told you, what I realized is that, so if we substitute all these as u, then we do not replace, did not use the replace twice. So anyway, it is already 4:20. We are going to take 4:21. We are going to take a short break, 15-minute break, and after that we are going to resume the second part of today's lecture at uh, at 4:36.